And we bring in PhDs and postdocs from around the world, and we work on challenges in space science and exploration with an interdisciplinary approach, bringing together machine learning researchers with space scientists. And together we work on some of the most interesting challenges of our time. So really excited to be here today with another one of our FDL teams. We are in week 7. So the program is almost completed, and I'm really looking forward to speaking with our Lightning team today. And I have with me here Emmanuel, Emma, Julia, and Satyarth. So thank you guys all for joining during this very busy week. So to kick us off, I'm going to start asking a couple of different questions. I'd also love to welcome our audience. Thank you so much for joining us. If you do have questions at any point in time, please send them to us, and we might have a little bit of time at the end for some Q&A. So with that, I would really love to hear from you a little bit more about the challenge that you're working on and why it's important. So I'm going to turn it over to Satyarth to kick us off.
Hey everyone. So to answer that question, it's quite simple actually. It's a rainy day, you look up in the sky, there's lightning. We just want to detect that beforehand. As simple as that. So to do that, some of the really smart people got together, spent $1 gazillion, put up really complicated sensors, devices, satellites up in the sky, precisely 32,000 something kilometers up. So it's in a geosynchronous orbit where it looks at a fixed region on Earth. So we have 2 satellites, GOES 16 and GOES 17, that looks at the US region, and like another one that looks at more of a Pacific Ocean region. So these 2 satellites look at the clouds, and the only task that these satellites have, the GLM lightning sensor mapper that we use, is to map the lightning events wherever they happen in the sky. And so yeah, our task is to take that raw data, crunch it, play with it, do a lot of mathematical, all the complicated theorems that all the smart people came up with, apply those to these data, and just figure out if we can detect lightning or predict storms a little beforehand. So right now, the weather forecastings or whatever, like the storms that predictions that we get or forecasting that we get is something around 30 minutes before the actual storm. So all these smart people come together just so that we can know 30 minutes beforehand that, yeah, there's a storm coming up, so we need to be prepared. And believe me, this is something that saves lives. This is the thing that makes some lucky people say that we got lucky, we got the warning on time. So that's our problem statement. That's what we're playing with.
Awesome. Thank you so much for the overview. And I live in Colorado, and we get pretty crazy weather here all the time. So this is really important for where I live, and I'm sure for many of our viewers as well, being able to understand the storms and everything that are happening sooner. So thank you. And then I would love to know a little bit more about the types of data that you're utilizing, where it comes from, and what it looks like. So Julie, I'm wondering if you can share some of that with us.
Sure. So I will share my screen to give some visualization. Yeah. So as Satyarth was saying before, our data comes from the GLM, so the Geostationary Lightning Mapper, which is this detector on board of GOES 17 and GOES 16. And what it does is that it actually takes a lot of pictures of a portion of Earth that covers the 2 Americas. And it takes pictures very often, every 2 milliseconds. And what it does is that it basically compares the value of each pixel with respect to a certain background value. And whenever the change, so the delta that we have, is bigger than a certain threshold, an event is triggered, same as you can see here. And it's sent vectors. So this happens for all the day, all the year. So we have actually a lot of data. And once this data is sent back to Earth, what you have to do is to try and dig the signal, the actual signal that corresponds to lightning, out of all the noise that you have. Because from the description of how the data is created, it's clear that together with lightning, you also collect a lot of noise that corresponds to different type of artifacts. So this data that is collected in the way I described is then packaged into netcdf files, which contain 20 seconds worth of data. And then this is the product that we are working with, which is raw data called level 0. If you want to see what, let's say, one of these netcdf file looks like, you can look at this picture in the center. So here we are plotting the content of one file, so 20 seconds of event in space and time. So the z-axis corresponds to the time dimension, and then the other two axes to space. And if you want to have a different visualization, so let's say you don't really care about the time component, but you just want to see the spatial component, you can collapse this data into 2D and have a look at what happens on the right. So if you look the picture in pink, this is the same file that you're seeing in the middle, but where the time is collapsed. And what you can see is that in some areas, there's a lot going on. In other areas, you only have a few scattered pixels. And if you zoom in and you look at the bottom picture on the right, you can see very small blobs. And this is what lightning looks like. And this is what we are trying to detect. So that's kind of the format of our data. It's kind of challenging to deal with it for several reasons. The first one is that it's very, very sparse. So here it doesn't look like that because we are looking at 20 seconds of data. But if you focus on a shorter time window, what you see is actually something like that, where it's basically nothing going on except for very few events that are scattered here and there. So the data is very sparse. And also, whenever you try to look for patterns, you really have to consider both space and time. So both the features are very important, and this adds complexity to the problem. And then I would say something else which is making this challenge particularly tough is that we have actually a lot of data available, level 0, completely raw, but we don't have labels. So we don't know in advance for data that were collected in previous years, what is lightning and what is not. So this makes the problem falling into what is called unsupervised learning, which is normally more challenging than supervised learning. And yeah, that's kind of the main challenge that we're facing in our project. So that's, yeah, kind of what our data looks like and the challenges that we're facing.
Thanks, Julia. That was a great overview, and Satyarth made it sound so like simple, and then to really find out you've got all these other things you have to worry about: time and space, unlabeled data, and just sparse data sets. So that's really, really interesting. One of the other questions that I have is if you could talk a little bit about the current lightning identification techniques and how your methods are going to advance the state of the art. And I'm wondering, Emmanuel, if you could kind of talk to that.
Yes, sure. Let me just share my screen real quick. And so in traditional sense of what is the standard, at least in the pipeline that we were comparing against, they sort of use a filtering technique. So the data, as Julie mentioned, is very noisy, quite sparse. And the definition of lightning, right, is kind of a very difficult question. Depending on which expert you talk to, we get different answers. So what typically they do is they do sort of filtering technique. And what it is it's easy to say something that is not lightning because it's either too noisy, it's too anomalous, it just kind of makes no sense, so on and so forth. But what we're trying to do is more of a machine learning approach where we try to look for structure, right? So we're not exactly looking at things that are not lightning. We're trying to see what is lightning, right? So we kind of switch the problem. And by doing so, we have to use a different sort of technique. So instead of filtering, we're doing more of, compression, dimensional reduction, clustering, and these sort of things. So as you can see on my screen is kind of the machine learning pipeline from a machine learning perspective. Where we have dimensionality reduction, we say, okay, we would like to compress this data. We're not looking for noise. We want to look at the lowest kind of structure. We really want to know, like, if there's lightning, so to speak. And then we have clustering where we say, okay, now that we've compressed the data, we want to identify the specific features based on similarity, for example. And last but not least, the visualization and the performance metrics. So we hope, not just black box models, we want our models to be open. We want people to be able to see and kind of understand what are the decisions we made, why we made them, and does this add some sort of insight to the actual experts, right? So, for us, kind of the thing we bring actually is kind of a machine learning perspective overall, and we're able to introduce, many different techniques under these different categories. I hope that answers your question as far as, the difference between, what was done and what we're doing, just in the in how you actually define the problem. That says a lot. So, yeah.
Yeah, that was a really great explanation. Thank you so much, Emmanuel. Really awesome. And looks like we have a few viewers from Venezuela, the UK, Canada. Welcome. Thank you for joining us. So the next question that I have is, you guys have been working for 7 weeks now, and I know you guys have been doing some pretty exciting things. So I was hoping that you would be able to share with us some of the initial results. And Emma, I'm hoping that you might have something to share.
I'd love to. Let me share my screen here. Can you see this all right? Yeah,
Yes.
okay. So my buddy Emmanuel just showed you this flow chart. So this is sort of our overall pipeline here. And what I'm going to show you now are some preliminary results for the first 3 items on our list. So we'll start with dimensionality reduction, which is where we take our raw data and we try to find a meaningful but smaller representation of it, because the raw data, as Julia mentioned, is quite large. So if we can make it smaller, it can be a little bit faster to perform computations over it. And it can also sometimes help you find patterns in the data within. So one thing we've been using to do dimensionality reduction is what we call an autoencoder. Just in case folks aren't familiar with it, that's no problem. The basic idea of what it's doing is we're sort of taking in a picture and we're sort of sweeping a filter over it. And as we do that, we compress it down into a smaller but equivalent representation. So just a smaller set of numbers that describe this picture. And we look at the smaller representation, we call that the latent space. And then we're going to take that and we're going to cluster that representation for every image, every piece of data that Julia showed you earlier. I'm going to save what that looks like for the end of this presentation, but first let me introduce what clustering is, or actually, sorry, first let me show you how we've been training this model. So we've been doing what we call hyperparameter sweeps. That's just where you're trying to find the best set of parameters for your model, so you get the most data, most information out of your data. So we've been trying lots of different sizes for our latent space. We've been trying different learning rates. How quickly do you take steps towards your optimal loss function? We do different kinds of transformations on the data. And so, some of those perform very well and some of them don't perform as well. So we're sort of looking for the best inside of that. And then here on the left, you can see we've got our model is able to take in an image, and then we look at how well it can reconstruct that image from that latent space. And that's kind of a good measure of how well we've learned the information that it contains. So here you can see we're able to pick up some stuff. Maybe our reconstruction isn't perfect yet, but we're working on tuning it this week. So now, as I said, let me introduce the idea of clustering and how we visualize the results of the clustering algorithm, and then I'll show you what that looks like on our autoencoder. So first, thinking about our raw data, if you remember the pictures that Julia showed you, we can take those and run them through different clustering algorithms. In this case, I'm showing you something called a k-means algorithm. And you can see that each row here are images of samples that were pushed into the same cluster. So the algorithm says, I think all of these pictures are about the same. And that's kind of interesting. We looked at some of these and we said, well, we are able to find pictures that look kind of similar. Often we see pixels that have lit up and they all seem to be in the same region of the image, and the algorithm can't really seem to tell the difference, or it seems to think that there's a lot of important difference between pixels that happen in the southeast corner versus, say, the southwest corner or something like that. And we're not sure if that's really what we want. So we're saying, you know what, this is how clustering works, but maybe raw data isn't the best. Maybe this is a great opportunity for us to apply these more advanced techniques. So to show you what the same clustering algorithm looks like, but on our more advanced autoencoder, like this more advanced representation of the latent space, we're starting to see clusters form, and the colors represent different labels that the clustering algorithm applied to all the data points here. And so we're starting to see that maybe we're finding some patterns in the data. Maybe we're able to distinguish between lightning events, or between data that represents lightning and maybe data that represents noise. So this is something we're still actively working on, but this is kind of how we're getting a sense of what we're doing and what we're learning with our current models.
Great. Thank you so much, Emma. And I'm really looking forward to the final presentation at the showcase to be able to see where you guys end up and where you guys continue the work from there. So really appreciate you going through some of the initial results. So now I'm going to switch gears a little bit and ask all of you a couple of questions. And also we have a few more audience members: Prague, Switzerland, California. Welcome. Again, if you do have any questions, please feel free to send those over to us, and we might be able to get to some of them at the end. So I would really like to know why you are personally interested in this challenge. I know that I am personally interested in it because I would love to know when things like lightning are going to happen in advance. So, but I would love to hear from you guys. So who would like to kick us off here?
I can take that. Well, I think my opinion is a little biased. I did FTL last year, and I love meeting these people. It's like we are literally connected around the globe. Our team is constitutes of Europe and US. Sometimes people from other side of the US, and sometimes there are mentors connecting from the other end of the world. It's amazing how you learn things, and there's a massive range of things you learn, because there are people from extreme scientific domains, there are people from machine learning, AI domains. You learn a lot of things. And why this problem specifically? Well, as I said, it's a rainy day. Look up. Well, I'd like to know a little before then, like when I'm actually walking in rain. As Sarah said, it's really cool. It's fascinating, because if you imagine how much time, effort, and manpower we all invest just to know that we could know 30 minutes before something critical is about to happen. And I think that's mind-blowing. So that's my motivation.
Thanks, Gareth. Yeah, it's so so important, and also it's great as well, as you mentioned, being able to work with people from all over the globe, and you guys are getting to work directly with Lockheed and NASA on this project, so it's pretty awesome. Emmanuel, do you want to go next?
Yeah, so for me, it's a bit of more of a personal satisfaction. So I come from a traditional machine learning background. So we don't get to apply all these really cool schemes to real problems, right? And so for me, it was kind of a bit of a validation to say, okay, let's see if we can talk to domain scientists. Let's see if we can get our head around the problem. Let's see if we can put it in machine learning terms. Let's see if we can have good communication. Let's see what the outcome is, because I think machine learning can really make a difference in the Earth observation, climate change, these sort of things. I really do think it can make a difference. So if it starts with lightning and ends with predicting the temperature in the next, 100 years, I'm quite satisfied. So I really think for me, it's more of a personal investment to really see what machine learning can do. So.
That's great. Yeah, and interdisciplinarity of FDL definitely allows for that. So I'm really excited to have you. So Julia.
Yeah, for me, it's kind of similar to what Emmanuel said. So during my PhD, I've always worked with very theoretical topics. It was more about proving convergence of algorithms or statistical guarantees. So I kind of had a lot of theory and then a small algorithm that only worked on, let's say, very clean and nice data sets. And I really wanted to get the chance of seeing what machine learning can do on a real problem, which is very real, very important, and on real data, where, as we described before, you don't get a nice MNIST data set with your digits, but you just get a ton of noise and you have to do something about it. And And also similarly to what Satyarth said, I wanted to experience a bit the idea of working very closely with a team, which is with people coming from different backgrounds, and rather than doing more like a research on your own, which is what the PhD experience was about for me. I really wanted to get the chance to collaborate, and also the idea of having something which is like intense for 8 weeks. I think it's kind of cool.
Thanks. Yeah, that's great. And it is really cool working really closely with a team for like a 4 for 9 weeks. It's really incredible. So thank you, Julia. And Emma.
I really resonate with what all my teammates have said already. I think I agree with all that, and that reflects a lot of my own experience. I think the one thing that I've noticed, I came in sort of thinking, I have some machine learning techniques that I've always wanted to use. Maybe they'll be applicable here and I can explore them and do that while working alongside. Really, these are some of the smartest people I've ever met, and I've learned a lot over these 8 weeks. But the other thing that's been happening as I've been going through the weeks and talking to people on this team, people on the other teams, watching the teams present their work, and frankly, just watching the news about weather and climate change right now, it's kind of coming to the forefront for me, like how important it's going to be not just studying the climate, but getting ready to respond to things that are going to happen. We're seeing floods, we're seeing fires, we're seeing all these things occur. I think it's making me wonder, maybe this is something to spend more time on in my career, to look into how can we use machine learning to make to sort of defend against things that are going to happen with the movement of climate change, and hopefully find ways to slow it or reverse it as well.
That's really wonderful. Yeah, really exciting work. So I'm going to go ahead and ask another question for this group. We learned a lot during FDL, and I would love to hear from all of you. What is one interesting thing that you learned from FDL? This can be like an interesting fact. Like this week, I learned that not all stars have atmospheres, and would be really interested to hear from you what you guys have learned. So to kick us off, Satyarth, you want to go again?
Yeah, sure. I mean, I haven't learned something as, I was involved in the project, so I didn't get to talk to a lot of people about cool things like how stars behave and their properties. But one thing that I did learn, I am a shortcuts guy. I like keyboard shortcuts and everything. And the number of tools and tricks you learn in FDL, I have never learned anywhere else. So that's mind blowing. And apart from that, there are amazing people who come and give brilliant talks. Like today in the wormhole event today, there were people who came and gave talks just about finding aliens. And like this is the nicest thing about FDL, because I could literally say that I'm still repeating the sentences I used to say when I was 10 years old. 10 years old, I was excited about aliens, and I still am, and I'm working about things that are related to that, and that's amazing.
Exactly, Arth. Yeah, it is really cool. And one of the fun things that we do is pro tips. And so we get to learn all of the interesting tips that people have learned from several years of experience in various different backgrounds. So that's been pretty neat as well. And Emma, would you like to go?
Yeah, I totally agree with Satyarth is the shortcuts guy. So it's really fun to get to pair program with him, because I'm like, oh, how'd you do that? And my answer would be very similar to his. I think it hit home how much I had learned when the other week we wanted to try this other model. Sorry, I opened up some code on GitHub, and I wanted to see what someone else's kind of code base looked like. And I come from a non-traditional background. I didn't do computer science as an undergrad. I didn't spend a lot of time studying it for years and years. I'm still relatively new to the field. I'd like first to say, if you are relatively new to the field, you can still do this, and this is a great place to learn and get exposed to new techniques. And the folks here are wonderful about teaching you, especially your teammates. And I really realized that when I opened up this code base, and usually I open them up and I'm not really sure why things are in certain folders and I don't really understand how to read all the code. I kind of run stuff until I can figure out how it works. But I opened it and I thought, oh, I know exactly why this repo is organized this way. I know what to expect to find in this folder. I know how to read the code. I opened up the script. I was like, oh, okay, it does this, this, this. Okay, they're using these packages. I've used those. Okay, cool, got it. And then I ran it. And that's never happened to me in my whole life. That would have taken weeks for me before. But thanks to the people in this room, I was like, oh yeah, this is a breeze now. So I think I really want to thank my teammates because that's where I've definitely learned the most.
That's an amazing experience, and kudos to all of you guys on the team for making that happen. And then Emmanuel.
Yeah, so actually I'm cheating a little bit because it's kind of based off my previous answer to the previous question. But if you recall, I was talking about like I have a personal investment in trying to understand real problems. And it amazes me every time I do something with FDL, like every single thing in the machine learning field that we try to avoid, like the plague, sparsity, noise, scale, is in every single real data set without fail. Like it's amazing how messy, how difficult these data sets are. And it really, for me, it kind of gives me a lot of respect for the people who curated them, the people who work through them, the people who try to understand, and like really they deserve just so much more and just kind of technological fields. And so I definitely gain a lot of respect for people who are able to do it, but I also get a lot of respect for people who are able to use this and actually make something useful out of it. Because like we said before, this isn't a cute IMNIS data set, right? This is something real and dirty and difficult. And I think that's like, for me, it always amazes me every time we come to FDL where people come, experts come and give us these data sets and say, go. And we're like, wow, this is pretty horrible. You know, like that to me is quite amazing. And, you know, I don't say it as a way to deter people. I say it as a way to, you know, come ready. It's going to be very interesting. It always is. So.
Yeah, that's a really good observation. We definitely work on messy, difficult problems and tackle them. So thank you. And Julia.
Yeah, I also resonate with what the others said. And building up on what Emma was describing, it was kind of the same for me because I realized how important it is to have like a sort of clean code, well organized that you can share with other people. Because if you code on your own, normally you have like, I don't know, maybe I shouldn't say that out loud, but you have like a lot of files, different versions of the files that only you understand. But when you are in a team, it's very important to have a sort of a hygiene and maintain a clean repo that everyone can understand. So that's something, yeah, that I thought was very valuable to learn. And as you were saying, during the pro tips is where I learned so many things that I can't even count them. And to share something related to Lightning, like I did mathematics and computer science, so I really have no expertise and no knowledge about the more Earth science related phenomenon. But we had a session at the very beginning of the sprint where we had a sort of ask the experts. And one of the experts, who is a domain expert, was explaining how when you have lightning, it's not only from the sky to Earth, but let's say the charges also builds from the building upwards. And he showed, this is not very precise, I'm sorry, but I just wanted to say that because I thought it was incredibly cool to discover. And this expert showed us, some awesome pictures that he captured. And I thought that was also something very interesting, like completely unrelated to my previous knowledge and expertise, but something very cool to discover.
That's a really good item that you shared with us, and it actually leads us into some of the questions that we're getting here about the different types of lightning that you guys are looking at and everything. So it sounds like you guys have been able to get a lot of insights from the experts. I don't know if there's any other comments you guys want to share about the type of lightning that you guys are looking at. Or that you guys are just getting really great insights from Lockheed. Go ahead, Julia.
Yeah, so none of us is the main expert. So we are let's say, more tackling the challenge from a very machine learning computer sciencey perspective. So we just take our data, and at the moment we are still in the machine learning part. So when we go to the interpretation, we will discuss experts. But for example, I think I remember from our Ask the Experts session that you can have not just, let's say, from sky to ground lightning, but also intra clouds. And that's something that I didn't know. And those are two different types of lightning that I think at some point would also be cool to discover, like, let's say, in terms of data, what are the differences in the patterns, even though it's not going to be, let's say, something we deliver in these 8 weeks, but for future developments, it's something that it's going to be interesting.
It's really great. That's awesome that you're being able to interact with the experts, be able to understand a little bit more about lightning. And then you also have, the potential to work on future projects with different types of lightning. So I think that kind of answers some of our questions that our viewers are asking. So we are about at our time. Satyarth, did you want to add anything?
Oh, no. I just seen comments. There's a question stating that, are there possible applications to predict lightning that causes severe fires? I just wanted to add a thing that at this point we're looking at data, and it's so sparse, and so it's literally like a massive space with dots in between. So it's so hard to understand, but it's at this point every lightning is like millions of volts. So I think if it falls on Earth, and if the surrounding area encourages a fire, I think every fire would be a severe fire. But specifically in terms of predicting using some smart algorithm, I think if we augment this lightning data with some Earth features like surrounding temperature, or like electricity conducting environments like a lot of trees or dry area or something, I think, yes, it's possible to build such an application, and would be really helpful for that matter. Yeah.
Awesome. Sounds like there's some interesting possibilities for the future, but you guys are doing some amazing work this summer. And again, I'm really excited to see what you guys are presenting in the showcase. So I would like to thank our Lightning team. You guys did amazing and shared a lot of interesting things about the work that you're doing. I'd like to thank our audience for tuning in. We are also going to be coming back with our FDL Europe teams, so stay tuned for more SETI Lives. And thank you so much for joining.